All right, Chapter 7, Brake Textbook Review. We're going to start out with number 19. 19 has a wheel where we've got just two forces applied directly to it. So we've got this 20 Newton one over here, and we've got this 30 Newton one over here. We get that the wheel's diameter is 4 centimeters, or its radius, which is going to be more important, is 2 centimeters, which is 0.02 meters. So force, we should immediately convert to torque, and we have two individual torques. Our end goal in number 19 is to find the net torque. So the 30 Newton one by itself, using torque equals force times radius, would get me 30 newtons times the 0.02 meter radius. 30 times 0.02 would be 0.6. And that's Newton meters. That would make it go clockwise by itself. Over here, torque is force times radius again. I've got 20 newtons of force, still 0.02 for my radius, so my torque is going to be 0.4 Newton meters. This force, and therefore this torque, is bigger. So to find net torque, I'm going to do bigger torque minus smaller torque, so 0.6 minus 0.4 gets me 0.2 Newton meters, and that is my net torque. Just like net force, right? You have one force pulling to the right, one to the left, and the right's bigger. You're going to go right minus left. Here we're going to go clockwise bigger minus counterclockwise smaller. Okay, number 31. Number 31, we get that we have a 2 kilogram horizontal rod. It's broken up. It looks like our pivot is a quarter of the way through here at the 25 centimeter mark. And we have 75 centimeters remaining. The problem asks us to find the gravitational torque around this point. And this is probably just a phrasing issue. All that really means is, what's the torque caused by gravity? Force of gravity is going to be the only force here. Now, we could certainly break this up and say a quarter of the mass is on this side and put that at the center here, and then 3/4 is on this side and put that at the center of this side. But way easier is to take advantage of the center of mass. We can always say that the entire force of gravity acts at the center of mass, and this thing's a meter long, so the center of mass must be the 50 centimeter mark, which is 25 centimeters away from the pivot point. So all of our force of gravity we can draw as acting right at the center of mass point. And again, 25 centimeters away, meaning 25 centimeter radius when we find out the torque, which is what we have to find, right? We have to find gravitational torque. So torque, force times radius. Our force is a force of gravity. So that's mg, the mass, 2 kilograms, which was given, and then 9.8. So my force is 19.6 newtons. So my torque is going to be 19.6, the force of gravity, times the radius, 0.25 meters. 19.6 times 0.25 should be 4.9. And 4.9 Newton meters is our gravitational torque. All right, number 46. 46 is kind of a complicated problem. We've got a couple different steps here. We get a 200 gram, 20 centimeter diameter, so cut that in half for radius, plastic disc. Right away when I see that, I see a mass, radius, and shape. I'm thinking moment of inertia. Spun on an axle by a motor. We want to know the torque that the motor is going to have to give us. So we're looking for torque. And then we know that we want to go from 0 to 1800 RPM, so initial and final angular velocity, and a time of 4 seconds. So I see that, I'm immediately thinking kinematics, right? Anytime you get an initial angular velocity, final, and a time, all kinematic variables. Relating together, torque, which is what I'm finding, moment of inertia, which I can find from my shape, mass, radius, and my kinematic stuff, is Newton's second law for rotation, net torque equals I alpha, so I definitely want to use this. Right, this will directly give me torque, which is my answer. I can find, and alpha I can find, so that's where I'm going to start. Let me go back to my givens. Mass is 200 grams. or 0.2 kilograms. And again, it said the diameter is 20 centimeters, so radius is 10 centimeters, which is 0.1 meters. And it said disc, right? Shape is a disc, which is like a cylinder. So I is 1/2 mr squared from your blue sheets. So I is 1/2 times 0.2 times 0.1 squared. We'll just use a calculator, make sure we don't make any math mistakes here. 0.5 times 0.2 times 0.1 squared. 0.001 kilogram meters squared is our moment of inertia. Separately, we get some information about kinematics. Omega I is 0, starts at rest. Omega final. Final angular velocity is 1800 revolutions per minute, RPM. So we'll convert that. In 1 revolution, there are 2 pi radians. And of course, in 1 minute, there are 60 seconds. So 1800 times 2 pi divided by 60, 188.5 radians per second is omega final. And we also get time is 4 seconds. I need to find alpha to use my Newton's second law equation, so let me use a kinematic for that. Omega final equals omega I plus alpha t. 188.5 equals 0 plus alpha times 4. So 188.5 divided by 4. It looks like my angular acceleration is 47.1. And that's radians per second squared because I used the right units over here. So now I can go back to Newton's second law. Net torque equals I alpha. Net torque, which is what I'm finding, torque from the motor, is 0.001 moment of inertia times 47.1 for alpha. So just move the decimal 3 places. Net torque is going to be 0.0471 Newton meters. There's 46. And our last one, 51. Anything past this, the 52, 65, 68, 69, don't worry about for the quiz. We'll come back to those later this week. But 51 we definitely want to look at. So let's read through it. Toy top, diameter again, 5 centimeters, so we'll cut that in half for a radius. Has a moment of inertia of 3 times 10 to the minus 5th kilogram meter squared. So we don't need to worry about shape. We just get moment of inertia right away. We don't have to use any of our formulas or blue sheets for that. It says that the string is pulled with a tension of 0.3 newtons, and that gets the top spinning. So that looks like it's going to be providing a torque to cause our angular acceleration. We want to know how long it takes, so time, to complete 5 revolutions. So right away I'm thinking I need to find time. That's in kinematics. So I'm going to have to find alpha here. All right, I get some information about moment of inertia right away. I get some force information, so I can use that to find out about torque, which means I'm going to find alpha, and then once I know it, I can find time. And in this last part, the string is long enough that it's wrapped around the top more than 5 turns. That just means that this force, and therefore the torque, is being constantly applied for the entire 5 revolutions that we care about. So essentially we can use Newton's second law without worrying about that. Let's write down all our given information. There's a lot of it here. I'm going to write down radius is 2.5 centimeters, or 0.025 meters. I'm going to write down moment of inertia is 3 times 10 to the minus 5th kilogram meters squared. I'm going to write down that my force is 0.30 newtons. I'm going to write down that theta is 5 revolutions, which is 10 pi radians. So let me get that as a decimal. 31.4, of course, 10 times pi. And anything else? No. So in the end, I want time. I suppose I also know actually that omega initial is 0, so it's starting from rest. Again, this is a net torque equals I alpha problem. Time is going to be inside alpha, right? So I got to find alpha that using this. I should have enough info for torque, and I was given I. Right, so let me find out torque first. Torque is force times radius, 0.3 times 0.025. So my torque is going to be 0.0075 Newton meter, so some small numbers here. I can use net torque equals I alpha now, so 0.0075 equals 3 times 10 to the minus 5 times alpha. Solve that for alpha. Alpha is 250, so angular acceleration 250 radians per second squared. Now I got to find time using kinematics, so I know alpha, I know omega initial, I know theta, and I want to know time. So the kinematic that involves all four of those and not our missing omega final is delta theta equals omega it plus 1/2 alpha t squared. Since omega initial is 0, this whole term will drop out. 31.4, or 10 pi, is theta. 1/2 times alpha, which is 250, times t squared. I can solve this for time. So we'll go 10 pi divided by 1/2 divided by 250. That's t squared, so take the square root of that. Time is 0.501 seconds, or half a second. Hopefully this helps. Let me know if you have any more that you want me to go through and solve out for you.